Green's Theorem, Part 1. In this video, we're not going to do any problems. Instead, we're going to look at a very important result from multivariable calculus called Green's Theorem. We're going to talk about the theory and try to get an intuitive feel for what's going on. So consider C, which is a positively oriented, piecewise smooth, simple closed curve. Those are our conditions. At least some of them. Don't get hung up them too strongly. The one I'm going to concentrate on is closed curve. But also let D be the region bounded by C. If P and Q have continuous first-order partial derivatives on an open region that contains D, then the line integral, which we could write as integral of f dot dr over the curve, or the integral p dx plus q dy over the curve, equals a double integral over the domain or the region bounded by the curve of the partial of q with respect to x minus the partial p with respect to y. Now, let's go back just briefly and revisit this idea where we have a function of xy gives us a gradient. So if I have a function of xy which gives a gradient, which is a particular vector field, right? We call this type of vector field conservative. And in a vector field such as this, which came from our gradient, we know that the partial of q with respect to x is going to equal the partial p with respect to y. So, if we have a simple closed curve, that's why I want to concentrate on that one, and we have a conservative vector field, then this double integral will always be 0. That's not the main result. But what I want to talk about is what happens if this back part here, this integrand, does not equal 0. So I'm going to jump ahead in the textbook technically, because I want to talk about an idea called curl. And we'll hit that formally pretty soon. Curl is something which we write as the del operator cross our vector field. Now, the idea of curl is something along these lines. At least this is the way I envision it. So pretend that I have a vector field. I'm just going to draw one that looks something like this. And maybe out here a little bit stronger. But the idea here is that I have this rotation in my vector field. Notice that this rotation or this vector field is curling, if you would. That's the way I imagine a curl. I usually think of this as having some sort of rotation. Let's get a representation of this in 3 dimensions. So you have xy here first, and then my curl is going to be in this xy plane, something like this. Just say it's revolving around. Now, have you ever heard of the right-hand rule? Perhaps from physics, where if there's some sort of rotation going around, we get a component that goes in the z direction. So the right-hand rules usually we do like fingers in the right-hand rule. These are my fingers that are wrapped around, and this is my right hand if you couldn't tell. And then my thumb points up in the direction of motion. So there's something happening here when there's rotation in the plane that gives a component that leaves the plane, if you would, and goes into the third dimension. There are ideas of this with like magnetic fields and electric fields. We're not going to get into all of that, but it might help you understand this if you've seen things like that before. So kind of a brief aside, maybe two, is notice that when we have this rotation in the plane, this vector field, I'm going to call it a force, is not conserved completely in the plane. So when we have this rotation, the force isn't conserved, meaning we don't have a conservative vector field. To me, that's where the name came from. I wasn't there in the meeting when they decided, but this is what makes sense to me. The other idea, kind of curl, is if you watch my previous videos, I usually talk about a function, f of x, y, as being like a mountain. It's a fixed thing. If I have a conservative vector field, which came from a function, right? I have this fixed mountain. But if I have this rotational vector field that's trying to describe my mountain, it's like my mountain is shaking and twisting and doing all sorts of things. So I'm not conserving my structure either. All right, enough of that. Let's do just a brief talk about curl over here. What does it mean to be del cross F? So this is going to be the determinant of the following matrix, I, J, K. And then the del operator is the partial with respect to x, the partial with respect to y. And since we're in the plane, I don't have anything over in the z. And then my f will be p, q, and then nothing in the k direction for this example here. Let's do the cross product of this. So we have I, and then we're going to have this times this minus this times this. So we're going to have I times 0. And then minus j, if you remember cross products, we'll have j times 0. And plus k times what? Well, now we have the k thing, which is the partial of q with respect to x minus the partial p with respect to y. So if we have a conservative vector field, this part of our double integral is 0. There's nothing kind of being extracted or coming out of the plane. But if we have this curl, even on a closed curve, then we have a component not in the x or the y, but in the z direction. So that's kind of the first level of understanding. There's another type of understanding that helps me see where this integral comes from just a little bit better. So I'm going to go back and rewrite Green's theorem, and I'll put this version down. We have this integral, the single integral over the curve is the double integral over the region of the partial of q with respect to x minus the partial p with respect to y. And then dA, which I'll put down as dx dy here. So what's going on here? Okay, let's imagine two very small rectangles side by side in the interior of D. Now I'm going to draw them a little bit bigger so we can see what's going on. And then imagine them touching, but I need a little space just so we can see what's happening. And also imagine that we have this internal rotation going on, kind of throughout my region D. So we're rotating, just like this. You might say, well, they're not all rotating exactly like that close by. Well, they are if things are small enough, okay? So we have this rotation. Now suppose that we want to integrate over dx dy. Well, what's happening? Down here on the bottom part, right, we're going this direction. But on the rectangle right next to it, should be touching, the rotation is the opposite direction. Like that. So what's happening here is that we have this internal rotation that's always canceling each other out. If I were to draw another dx dy, little tiny rectangle right next to it, with the same rotation as it would be very close by, notice that this piece and this piece, because of the rotation in opposite directions, those pieces would be canceling each other out. So all the internal stuff cancels each other out. What's the only thing that doesn't get canceled out? Well, it's simply all these pieces right on the boundary. So that's one way, or another way of looking at Green's theorem, where this is going to represent my internal rectangles, and I will realize that the internal rotation cancels, leaving me only the stuff on the boundary. Now, what does that mean practically? Does that mean that we will always use this? No, we might, but we're going to see shortly that sometimes this double integral is actually easier to evaluate or to set up than the single integral. But the point is, we have a choice.